Hello, welcome back to the next video. I lost the hat's over there. You get to look at this dead trim. I'm currently in Jeff Cakes. I'm going to finish this one and then we're going to do, as you can see from the title, Algebra Lecture 4. Oh, there's someone right now in like the top 40 or something. It's so loud. Vibrating through the entire building. So you might hear their music. Hopefully it's not loud enough to be copyrighted, even though I don't make any money off of these. But just so you know, it's not like you can't hear music from your end, it's from my end. Just I think they're right there. So they might be one of the many things. They're definitely upstairs, I just don't know which one. Anyway, Algebra Lecture 4. This one is a pain in the ass. You know, I can barely understand it. I understand it now. It's got a message from someone from my flat telling other people to shut the hell up. Nope, it's someone wanting kitchen scales. Whoops. I don't have any anyway. No, so this one's going to be, yep, lecture 4. There are 4 definitions, the proof involved. So yeah, let's just get started because I've got at about past, I'm going to go and make some dinner. So I'm going to make some soup, I think. You know, nothing fancy, with a bit of bread possibly. And yeah, I really need to do a food shop. I don't think I've got time tomorrow. I might be able to go after lectures. Who knows? It's up in the air. Anyway, Algebra Lecture 4. So we have definition 1.11. I don't think you need to know, from what I know, you don't need to know the names of these, you just need to know them. So I need to know that if A is subset B and B is subset of A, then it equals B. Something I need to know. I don't need to know which definition that was. Just need to know that it's a thing. Right. So the last video I did, we finished on functions. So that's like the f such that A goes to B. And this one kind of carries on with that. I'm going to go through a bunch of stuff that I'm not confident on, but I'm hoping that I'll be able to figure it out whilst trying to explain it. Let's go. So definition 1.11, if the function of A to B and the function of f A to B and function g from B to C are functions, you see I just said that, then the composite, we did composite. Oh, this is a recap then. So the composite GOF is GF of A. We did that last time. All right, definition 1.12. For any set A, random set, there's an identity function where the identity of A, so it's a ID for identity and then base A, so bottom right A, such that A goes to A. So it's a function such that capital A goes to capital A such that little a is mapped to little a. So what this is basically saying, because I went to this maths help thing for them to help me explain it to me. And from what I could tell, the identity A is basically pointless because it maps the set A to itself such that a point, an element from that set is mapped to itself in that set. It's basically saying that 1 equals 1 or A equals A is what I can gather from it. Then it does kind of branch off of that. So if you have the function f from A to B, and that's any function, then if you do the composite FO identity of A, that equals F, which makes sense because the identity of A means nothing. So you basically, where is it going? So that's basically f of the identity of A. Identity of A is nothing, so it's just f. But then f is equal to the identity of B of f. Now, I don't know how you'd write that, so I'm going to add it to, I'm going to get a different pen. This pen sucks. Oh, I've grabbed a highlighter instead. Fantastic. And the lights are charm. Fresh black pen. So this is lecture 4. Identity. Non-matrix, is it? What is it? Identity function. I know the identity matrix is like 1001. So then if you have the matrix 2-1, if you have the matrix 2-1-1-1, then timesing it by the identity 1001 would give you 2 1 1 1. So it'd give you the same thing. There you go. Basically, I think that I don't know. I need help with the identity. And this is what a lot of this video is going to be. It's me basically saying, okay, I don't know what it means. For instance, F composite identity A, that's F of the identity of A. You can write that. How do you write the identity of B composite F? Do you write, is it the same as, because here it was identity of A, identity, and then base A. Do you write identity base A brackets f of x? Or is it the identity of A, and then in the base it's A brackets f of x? Do read them and go on. Right. So for any subset x in A, so x is just a subset of A, there's an inclusion function such that inc, you don't write inc of f or inc of x, it's just inc, so inc for inclusion, such that x goes to A such that x maps to x. Now, I think the inclusion function is x is a subset of A, so everything is x, everything in x is in A. And I think this is saying, if you take x and you go to A, then the same thing going from x to A, it has to be the same because x is a subset of A. So this is always going to map, this element of x is always going to map to the same element in A because it's a subset. So it can do that. It has i.e. the graph, which we know is basically literally just a graph. The graph of the inclusion function is the set of the pair xa. There's people outside, so I'm gonna. Anyway, the graph of the inclusion function is equal to the set of the pair xa in x cross A such that A equals x, which is basically what this is. And this is basically saying you have an element in A, element of x, which is the same because x is a subset of A. And I think that's what the inclusion function is. The inclusion function is just saying if you have something which is a subset, one set which is a subset of another subset, one set which is a subset of another set, if you then map an element from the first one into the second one, it's going to be the same. It can be the same element because all of that is in that. That's what it's saying, basically. Right. So, and since we know the empty set is always a subset of any set, so if we say here the empty set is a subset of A, then for any A, no matter what set it is, there'll be an inclusion of the empty set to A. So the inclusion is basically mapping any subset to a set. From what I can tell, if you do, so B is a subset of A, inclusion B to A is saying that you're including all of B in A. So a subset, pretty much. Right. Additionally, the empty set times A, if you say this empty set times A is equal to the set of XA such that X is in the empty set and A is in the set A, that doesn't exist because X, well, so that equals the empty set. So anything times the empty set equals the empty set because it's basically times things by 0. Okay. All right. Ooh. So we know, I'm pretty sure we know G, I haven't written it down, but I think G means the graph. The only subset is the graph. Graph of the empty set is a subset of the empty set when the graph equals the empty set, which makes sense because of your A is a subset of itself because A equals A. So this is basically saying you can have a subset of an empty set if that set equals the empty set. Right. Definition 1.13. So for any X, for any subset of A, which we're going to denote X, where, and you also have the function of F going from A to B, then the restriction, which is kind of like when you do statistics, you have given. So you'd have the probability of A given B, which would equal PANB over PB. It's kind of like that. It's just a long line, like on the keyboard. Right next to the Z on the left, you have the, I think that's, you call that backslash. If you shift click that, you have the one line. That's what it is. So for this, you'd write, so X is a subset of A, and then we know the function F from A to B. Then F line X, which you'd read as F restricted to X, is so it goes from X to B. And I think what that restriction thing means is, as we know X is in A, all of X is in A. And if you're then restricting F to X, you can't take any of the rest of A because you're only taking X. And as you know X is in A, it can still go to B. It won't go to same amount of B, but any subset of A can still have a function where it goes from that subset to B because A can go to B, therefore the subset can go to B. And this is what the restriction basically restricts A to this subset, but it's still going to B because, you know, it would. Another way of saying this is F restricted to X equals F composite the inclusion of X. And we know the inclusion is basically going to subset A. So this is basically having, you have the function F, and then it's like you have F of X, this is the F of the inclusion of X, which is a subset. So restricted is basically restricting it from, so if you have X subset of A, A goes to B, and the restriction F restricted to X means that it's a subset going to B, and this is basically what F composite inclusion X means, is you have F, which is A to B, and then you're basically putting in X, inclusion, and as the inclusion is inclusion X to A, you have codomain and domain equal, and as we know, when you do that, you can bring it in. There's a little triangle. So if you have X, B, and A, to get from X to A, use the inclusion function. A to B, use F, but if you want to go straight from X to B, you can do F restricted to X. Right, so I need to remember stuff like that. So inclusion is when you include a subset going to A, and then restriction is when you're restricting a function where it's a subset from the inverse. Can be a bit remembering. I mean, if I do, no jacket. If I do questions on it, hopefully it'll stick in. I need to empty my bin. Right. You get to watch me. This is a bit mukbang. Right. I have to look at you, not me. My face is literally there instead of there, which is where you are. I'll try and look at you, but I don't know. When I'm FaceTiming, I always look at myself as well. I need a drink. Alright, there we go. You can see my sink right there. I'm going to fill this up. I'll need a little bit. Oh, but I don't trust myself. I don't trust myself. I'm getting a phone call, 1 sec. And I'm back. Yep. It's just my mum. I'll call her back after I finish this video. Bang out some revision. What I might do, I'll do with videos again. This is, you probably don't care, but I'm going to like so tomorrow I'll probably do like 2 analysis or methods or something, and then I'll what do you call it? I'll do one where I go over like all of the things I've done today. So I'll go over 1 to 4, lectures 1 to 4 of algebra, just to keep it fresh. And then, yeah, the following day I'll do analysis, and then I'll loop it around. So then when I get back to algebra, I'll then cover lectures 1 to whatever I've got up to then. I'll keep doing that. So by the end, I'll be able to go from 1 to 30 or whatever. So off the top of my head, which will be mint. What it'll be mint. Or I might split it into 2 because 30 is a lot. I'll be like, if 3 took an hour, that would be what, 10 hours? I don't think my laptop even has the memory for that. Anyway, off topic. Okay, so if you have the function f goes from a to b, the image of f is a subset of b, which makes sense because the image, if I'm not mistaken, which I might be, I'm thinking of the inclusion. What is the image? Oh, I haven't learned yet. Well, there you go. So you have the function f of a to b, the image, which is just im and then brackets f, subset of b, and then you write this as the image of f equals a set of b, little b in b, such that b is equal to f of a for a and a. So it's a different way. We went over this in the previous one, if I'm not mistaken. Something like this, where it was, if I can find it, where it's around the same sort of thing, where b equals f of a, or something along those lines. I can't find it now, but it's around that. So this basically means the image of f is a subset of b, such that when you have a random element from b, that equals function of a for some a in, for some function of an element in a. Right. Which a better way to say this is the set of little b in b, so an element in b such that there exists an element in a where b equals f of a. Right. I'm gonna add image to the list because again, dydw i ddim yn gwybod yn yr gwaith. And then they've added a random like tilde or something. Whereas like you have an F, then you have a little squiggly line over it, like tilde or something like that. And that's your function of F tilde such that A goes to the image of F such that A maps to the F of A. Because if the image of F is a subset of B, and we know that F of A equals B, so this is basically saying you have A mapping to the image of F such that little a maps to B, which is, that's basically image of F is the image of F is basically B. It's a subset, so everything in F is in B. So it equals some B, but it might not equal all of the B's. Is that what it's going for? I don't know. My hair, look how tall it is. It's ridiculous. I don't understand. Anyway, the F tilde satisfies the equation where you have F is equal to the inclusion composite F tilde. So the inclusion of F tilde, inclusion is a subset. So with your inclusion of F tilde, run over inclusion literally. Yes, subset, yeah. So the inclusion of F tilde is in a subset F tilde, which is saying that F tilde goes to B such that F of A maps to B. That doesn't make sense. It doesn't make sense. It doesn't make sense. Fine, I got a list. Man City game finishes at 10. What's that? That's an hour. Give me an well, I'll have a bit of time to tomorrow. I think let me check my calendar. I should have time tomorrow to actually go over it. It's good actually if I'm going through this and this will show me the things I need to look at, and the rest of it I should be okay with. Right. Like how professional I am. So Thursday 9 till 10, 10 till 11. And I have 2 hours. Then a tutorial, then 2 hours, and then a lecture. Right. 2 hour break. In that 2 hour break, I can actually try and go over all of this. Before the algebra tutorial, then if I'm still stuck in anything, then right. Smart. Big brain time. Let me click my neck. I didn't even click it. Fantastic. Right. Now we get on to the very important stuff that I'm a bit confused about. But before we do that, we have another triangle, because we had a triangle on the previous page. Another one of them. See if you have A, B, and the image of F. To get from A to the image of F, you have F tilde. You want to get A to B, that's obviously just F. If you want to get from the image of F to B, you can use the inclusion because image of F is a subset of B. So F tilde is mapping from one set to a subset of another set. So if you have F is just one set to another, F tilde is one set to a subset of that set. Okay, I think I'm getting the hang of it. I'll write it down, but I might not remember it. I'm looking at myself again, making eye contact with myself, even though I'm looking down on the camera. Right. Stop rambling. Definition 1.14 So if you let F if you let the function f from a to b be a function, then f is injective or an injection when for all x and y, so for all x and y in the set A, f of x, so this is two different elements in the set A, the function applied to one element equals the function applied to another element such that they equal each other. So it's injective if one element of A equals an element in B. And we know, we know that x equals f of y and y equals f of x. But then where's the b come into this? Oh, it says in more kind of basically child way of saying it, a unique element in A can map to a unique element in B. Right. So if you have 3 elements in A and 4 elements in B, each element of A can map to an element in B where it's the only one mapping to it. So you have 3 elements here, 4 elements here. You know, you can have these 3 there. They're each mapping to their own individual element. Doesn't matter that there's a 4th one still left. That doesn't matter, because at least everything in the function, everything in A is mapping to at least one thing in B. Right. Then you say f is surjective or a surjection when for all y in B, so for all of these elements in B, there's an element in A where f of x equals y, i.e. the image of f is equal to B. The image of f is a subset of B, so when it's equal, and from this one, what I'm pretty sure, because you can draw like potato diagrams, which is like a more visual way of learning it, and it's the way I kind of learned. You have 4 elements here, 4 elements in set A, and 3 elements in set B. Each one of set B can be mapped to at least once. The 3rd one down here, even though my pinky's not long enough, can be mapped to twice by both of these, but each one of these is being mapped to at least once, and that's what a surjection is. Everything in set B being mapped to at least once. Injection, everything in A mapping to an individual thing in B. So like this equals that, that equals that, that equals that. Whereas this is, and a good way to think of it, injection, x equals x. 1 equals 1, 2 equals 2, 3 equals 3. Surjection, it can be, it maps from x to x squared. That's x to x, this is x to x squared. Because you can have 1 mapping to 1, 2 mapping to 4, 3 mapping to 9, and then -1 can also map to 1, -2 can also map to 4, -3 can also map to 9. And that's a good way to remember it, which I hadn't thought of. So I'm going to chuck it in here. I'm just going to put some brackets around it. X. There you go. Small. Right. And then a bijection is both injection and surjection. It's like a mixture of the two. And that's pretty much when you have each element in B is being mapped to, and each element of A is mapping to a unique thing in B. So it's basically you have three elements each mapped to each other individually. That's pretty much it. So injective, everything in A is mapping to its own unique thing in B. Surjective, everything in B is mapped to at least once. And bijective, everything in A maps to a unique thing in B, and everything in B is mapped to at least once. So it's basically A and B equal each other, from what I can gather. Right. And some examples here. So if you have the function f going from the real numbers to the real numbers, such that x maps to x squared, it's not injective, as plus and minus 1 squared both equal 1. Oh, it's not such fudge. Well, that's wrong. And the pen has decided to break. Try this one. There you go. Right. So if you have a real number, some real numbers, just any number. Real number going to a real number such that x maps to x squared is not injective, as plus and minus 1 squared both equal 1, which means well, that's two things. It's not unique. It's not surjective, because minus 1 doesn't equal x squared. Now surjective is, does that make sense to me? What? Because I thought if something's surjective, more than one thing can map to it. Everything's mapped to at least once. And if it's x squared, it's going to be mapped to at least once. Let's say minus 1. Oh, of course, because x, if it's real to real, then x squared has to, the set of B, which is x squared, has to include negative numbers. And you can't have a square number that's a negative. Like minus 4. If you square minus 2, you get 4. If you square 2, you get 4. You can't have something squared equaling a negative number. Does that make sense? And it's not bijective, and it's neither injective or surjective. If it was, say this was injective and not surjective, it wouldn't be bijective because it has to be both. Right. So if x is a subset of A, then the inclusion function of x to A is injective, as the inclusion of x is equal to x, because it basically maps x to x. Which then means the inclusion of x is equal to the inclusion of y, because you say y is y the elements of A, x the elements of x equal each other, because it's basically a subset of that. Makes sense? But if x is the empty set, so, and the empty set we know can be subsets of any set, so it could be the inclusion of the empty set to A, it's still true, as there can't be, because to prove something's injective, basically you have to say x equals y, f of x equals f of y, therefore x equals y. Or the opposite of that, it can't happen, it can't be injective, or it's injective if x doesn't equal y, and f of x doesn't equal f of y. And as the empty set doesn't have an x to begin with, x can't equal y, so it means f of x can't equal f of y, therefore it's injective, because it's kind of proving the opposite. It's not proving that x equals y, therefore f of x equals f of y. It's proving that, because if it has to happen, so injectivity won't happen if x doesn't equal y and f of x doesn't equal f of y. And it's true here, because as there's no x, that can't even happen in the first place. X not equaling y can't happen because there's no x to begin with. And if that can't happen, then you can't disprove that it's a subset, therefore it's true. Again, awful explanation, but it made sense to me. 7 minutes, great. Right, so if you're given the functions f a to b and g b to c, if f and g are both injective, so everything from a maps to a unique thing in b, then gf of x, gof of x, or gf of x, sorry, I'll just say it like that, the composite, that's from a to c, and if a can go to unique things in b, and b can go to unique things in c, and a can go to unique things in c. If f and g are surjective, and so is gof, so if everything in b can be mapped to at least once by a, everything in c can be mapped to at least once by b, everything in c can be mapped to at least once by a. Makes sense because a can go to b, b can go to c, so a can go to c. And if it's bijective, then so is gof, because a equals everything in b, b equals everything in c, and a and c are the same. It's like a equals b equals c, therefore a equals c. And the proof of this, so we're first going to prove the injective one. If you have x and y in A, so x is an element, y is an element, both in A. Suppose that the composite, I'm not going to say composite, it's long. If you suppose that gf of x is equal to gf of y, because it's injective, we're going to assume that f of x equals f of y. Then you can say gf of x equals gf of y, therefore, if x and y are both in A, then you can suppose they're the same. So you can suppose that f of x and f of y are the same, because they're both in the same set. So then gf of x equals gf of y, therefore f of x equals f of y. And since g is injective, so you do. Okay, so you assume that f and g are injective in this scenario. So you're assuming everything in A can map to something in B. Okay. So then from that, if everything from A can map to B and everything from B can map to C, then we know if you do gf of x, that's the same as g of y, because y is in B. I think the way they do it is x, y, and A means y is in B, pretty much. Or x equals f of x, isn't it? So if you have g composite f of x, g composite f of y, I don't really understand that. A proof. Right, I don't really understand that one. Two more. Hey. So we know the bijective one is just a mixture of A and B, because, well, the injection is surjection 1, because that's what bijection literally is. So in the proof of B, if you have some element C, little c in C, which was what G went from B to C, then there exists a little b in B such that G of B equals C, which is basically definition of surjection. G of f of x equals y, G of B equals C. And since G is surjective, and there exists a little a in A such that f of A equals B, then you can say that the gf of A, well, gf of A is G of B, and we know G of B equals C, so then GOF is surjective, because, yeah, that one makes sense. That one makes sense, because you're assuming, so I think you're assuming f and G are both injective. So if A can map to a unique thing in B, and then you have x and y both in A, it's not that, it's both in A, meaning if x and y are both in A, then you can suppose that gf of x is equal to gf of y. unique value. Okay, unique value. So so f of x is an x and a y, a and b, and you're assuming that g of f of x equals gf of y. No, it is a proof. I don't understand it. Fine. Apart from that, so that's not horrendous. There's only 5 things I got stuck on. The identity function, I'm pretty sure it's nothing, but then I don't know how to write it. Let me just write this. I'm using incredibly poor English just so I can get it in. Right, the image. Yep. And that they can work together, and then x, y is meaning proof. There you go. That's algebra. Not great, but I understood more than I thought I would. I understood what injective, surjective, and bijective meant. I just got a bit confused, really. Anyway, that's it. Algebra. So for now, I'll go downstairs, chat to my flatmates about if you can see all of that. And yeah, that's the end of the video. In the words of Call Me Kevin, bye for now.